So hello, everybody, and welcome to this week's data-driven seminar series hosted by Coots and Brunton Group at University of Washington. Today's speaker is Andrew Stuart. He's the Brin Professor of Computing and Mathematical Sciences at Caltech. He received his PhD from Oxford University and held postdoctoral positions at Oxford and MIT before taking faculty positions at Bath University, Stanford, University of Warwick, and finally Caltech, where he is now. His research focuses on integration of data with complex models and inverse problems and stochastic modeling. And today he's going to be talking about supervised learning of operators. So with that introduction, you can take it away, Stuart. Thanks.
Thanks, Zach, for the very nice introduction. So you see the title here, Supervised Learning of Operators. This is a big field, which is relatively recent, but exploding quite quickly, and covers a number of different parts of mathematics and applications. I'm going to focus on telling you about why I'm formulating the problem, firstly, then telling you why I'm personally interested in it in terms of applications, and then showing you some of the math that's being developed to understand the field. And the work that I describe is collaborative. It's an overview of a large body of work. And I want to take this opportunity to give a brief literature review, but most importantly, to highlight my collaborators in this area who are in red. And also to say that I'm happy to make the slides available so you can follow up on references later on if you're interested. It's a simple PDF. And also that I welcome interruptions. So please interrupt me if you have questions.
Thanks, Andrew. And just so you know, they can't unmute themselves, but if they raise their hands, then I can interrupt and ask a question for them.
Thank you.
And unmute them. Thanks.
Yeah, so please do raise your hand and let Zach ask me questions, because it'll flow better if you interrupt me. So collaborators in this work are Kaushik Bhattacharya, who's a professor in mechanical engineering at Caltech, Bamdad, who is now at University of Washington and was a postdoc here, Nick Kavachki, who's just graduated, my first PhD student at Caltech, Nick Nelson, who is a PhD student at Caltech, Zhongyi Li, who is a PhD student in computer science here, Kamya, who's a professor at Purdue, Birgitte Liu, who is an assistant professor at Cambridge and was a postdoc at Caltech, and Anima, who is a professor in computer science here. Also, Margaret Troutner, PhD student here, and I think I have covered everyone except at the bottom, Martin de Hoop, who is a professor at Rice, Daniel Huang, who is a postdoc at Caltech in CLIMA, the Climate Modeling Alliance, and Elizabeth Chan, who is a von Karman instructor at Caltech. So I'm going to organize the talk in this way. I'll tell you a little bit about operator learning, and in that context, I will formulate the problem mathematically and show you applications that are of interest to me. There are many, many applications, but I want to show you the ones that motivate our work in this area. I will then describe in detail some of the algorithms that have been developed in this area and some of the approximation theory that goes with them, and highlight open questions. There are many open questions in this field. And I will highlight them in detail by finishing the talk with two examples. One, perhaps counterintuitively, the Navier-Stokes equation will be an example of something where the methodology works very well. And this is a simple problem from the perspective of operator learning. And I'll show you the advection equation, which is a difficult problem, linear advection, and highlight some of the open questions that remain in this field. Okay, so let me set up the notation. So I'm interested in supervised learning, which I will define, between spaces U and V, which are separable Banach spaces. And in particular, I'm going to look at the case where they are Banach spaces of vector-valued functions. So U will be vector-valued functions over dx, taking vector values in RDI, I for input, and V will be functions over dy, taking also vector valued of dimension do for output. And the problem we're interested in is determining an operator, psi dagger, which maps between these spaces of functions, given only information in the form of samples. So the samples here are un, which are distributed according to mu and are in the Banach space calligraphic U, and the image of un under psi dagger, which are then elements of V. So these are pairs, and together they summarize information about psi dagger. And the assumption of this talk, which can be relaxed, and relaxations are important, but for the purposes of this talk, the only information we have about psi dagger is comes in the form of these pairs of data points. And the supervised learning problem is to approximate psi dagger given this data. So it's a interpolation or regression problem. And what makes it specifically challenging is the fact that U and V here are Banach spaces of functions. Okay, any questions about the problem statement? So the data is drawn from a probability measure mu on the space of functions U, and this measure will play a role in what comes in the remainder of the talk. Okay, so this is a fairly standard problem if U and V are finite dimensional Euclidean spaces, or if U is a Euclidean space and V is a set of categories. This supervised learning problem is well studied and is one of the great successes of machine learning. And I'm going to describe to you just briefly the variants on training and testing that will underlie the experiments that you'll see later in this talk. So I'm going to try and approximate psi with a function, psi dagger with a function psi, which takes U into V and is parameterized by parameters theta, subset of Rp. So P is the dimension of the parameter space in which we wish to approximate. And I'm going to define the risk, which is the average over the data measure of the difference between psi dagger here and our approximation function psi. And we will choose theta. This is a conceptual idea, which I will approximate in a moment. We choose theta by minimizing the risk. So theta star is the smallest value that can be achieved for this norm on functions mapping U into V. So this is a norm, it's called the Bochner norm. And of course, as stated, we would need to know psi dagger and the measure mu. In practice, we don't know psi dagger, we know mu only empirically. And so this is approximated through samples. And the sample approximation, known as the empirical risk, is minimized to approximate theta star. So that's the standard methodology, and that's the one that we will adopt in this talk. And testing, slightly non-standard, I'm going to look at a relative error. So other than the fact that this error is relative, this is again a fairly standard metric for measuring for testing the fit at theta star having trained. Okay. So everything so far is standard supervised learning with the exception of the fact that U and V are Banach spaces of functions. So why am I interested in this in the specific context where U and V are Banach spaces of functions? There are two primary classes of problems that motivate me. One is the discovery of constitutive models or closures for problems in mechanics. And I'll say a little bit about that through means of an example. And the other is the design of fast surrogate models. So replacing computational methods for PDEs based on classical numerical analysis, replacing them with data learnt methods which are potentially faster than classical numerical analysis PDE methods. And I will show you an example of this. So why do this? I'm going to show you by means of example. Then high-level view of what to keep in mind and understand about sources of error in doing this. I want to do this accurately, and indeed, I would argue that scientific computing has been successful over the last 50 to 100 years, not only because of the empirical success that we've had in, for example, computing the flow round wing of an aircraft, or predicting material properties that are, or designing materials that have desirable properties. This has come partly because of clever computation, but also because of the theory that underpins. And so I think if we're going to use supervised learning in the context of what I would refer to as scientific machine learning, we need to understand the error that we commit when we approximate psi dagger by psi learnt in the way that I describe. And there are 4 sources of error. And in this particular context, where the input spaces and output spaces are functions, the first is discretization of the function spaces. The second is the effect of data volume. We don't have the entire measure mu, we just have samples from it. So n samples, what is the effect of the sample size? What is the sample complexity of the problem? The richness of the parameterization, the value of P, the dimension of the parameter space, but not only the dimension of the parameter space, but how we use the parameters, how we represent the functions. Clever representations can lead to more economical representations of psi dagger from the class psi. And then finally, the method of optimization plays an important role in determining how close one gets to the minimizer of the risk, and therefore the optimal choice of parameter. So I've highlighted the red because in this talk, I'm going to concentrate mainly on those 2, and indeed primarily on parameterization, the second one. But all of these are important, and I will also show evidence for the approach that we use being invariant with respect to discretization, and therefore suggesting a method for avoiding issues related to discretization of the spaces. Okay, so I will mainly concentrate on parameterization, and if there's time or questions, I can show you material relating to data volume. But this is a hard subject because all of these interact. So from a theoretical point of view, one has to understand numerical analysis questions in approximation theory. That's the first and the third bullet, statistical learning, and optimization. Okay, let me start with an example to demonstrate what I mean by operator learning, and also to show you some of the advantages in terms of speed up that can be achieved. So this is an example from 2D incompressible fluid flow. NSE stands for Navier-Stokes equation. In this setting on a torus, firstly, we are on a torus. Secondly, we're 2D incompressible, and the equations can be reconfigured in terms of the scalar component of the vorticity orthogonal to the plane. And what is written here is a scalar partial differential equation for the vorticity omega involving the stream function psi and the velocity field v. There are standard methods for solving this, and the way we set the problem up is related to this paper of Chandler and Kurzweil. So we're going to use pseudo-spectral methods with fast time stepping as an integrator. The objective is to learn the mapping from the initial condition of the vorticity at time 0 to the solution for the vorticity at time tau. And the bottom line of what I'm about to show you is that we achieve speed up of around a factor of 500, which enables the solution of, for example, inverse problems in this context that were beyond reach without this methodology. So there's some technical details on here, for example, how the measure mu is designed. It's a Gaussian random field, and we have control over the tau is an inverse length scale, and delta is a regularity parameter. Again, happy to discuss those details with anyone who's interested, but the main takeaway is that we have a Gaussian random field, and it's defined through an inverse power of the Laplacian shifted by the identity, minus the Laplacian shifted by the identity. So this is what I'm going to show you here is a comparison between the solution using pseudo-spectral method of the equation on the previous slide for the vorticity and the prediction that we can make using a specific operator learning technique, the Fourier neural operator, which I'll describe in a bit later. In eyeball norm, the main point is that the top row here is indistinguishable from the bottom row. That's very loose, but that's the idea here. The idea is that we're able to replicate the dynamics of the equation by means of something which is learnt from data. The data is generated by solving the equation, but once we have learnt an approximation, it runs a lot faster than the original pseudospectral method. In this case, by a factor of 500 over a specific time interval. And that time interval is 50 and is the one used to solve an inverse problem, which I'm now describing on this slide. So we're solving a Bayesian inverse problem of recovering the initial condition from pointwise measurements of the vorticity. So here's the initial condition. And these circles here are the grid on which we measure. This is an ill-posed inverse problem in the similar level of ill-posedness as you would see if you try to invert the heat equation, for the same reason that the forward map is an analytic semigroup, and therefore inverting it is very ill-posed. Furthermore, we have a shortage of information in the measurements of the vorticity at time 50. We only measure on a grid, and there is noise in the observations. Therefore, a Bayesian inversion, which quantifies the uncertainty in estimates of the unknown, is natural. And this is a prototype of what one does through the 4D VAR method in weather forecasting, but here showing that we can get full Bayesian inversion. And the reason we're able to achieve that is because we've replaced solution of the forward model by a surrogate found rather than using the solution of the partial differential equation, psi dagger, which is the map from the vorticity initially to the vorticity at time 50, we use a trained neural network, which is evaluated around 500 times faster. So the original method took 12 hours, but we're able to solve it in 2 minutes and obtain similar accuracy. So the accuracy here is described in terms of recovery of the initial condition, the mean of the recovery of the initial condition, but we also recover the posterior variance and other statistics with same level of accuracy, 500 times faster. So that's the first example of why I would want to do this. I would want to do it because we can do things much faster this way, and that enables us to solve problems we couldn't solve before. Now I'm going to show you a different motivation, which is the learning of constitutive laws. And I want to frame this in the language of the fields of viscoelasticity and plasticity. So in particular, I'm going to be interested in multiscale problems. So these are problems which have rapid variation at small scales, and that rapid variation is denoted by parameter epsilon. So I'm writing here the equations of continuum mechanics. We have top row is balance of linear momentum. So this is just F equals ma on the left, and on the right, the forces, and F body forces, and then internal forces. One has the divergence of the stress tensor. And a wide class of problems in viscoelasticity and plasticity, the relationship between, sorry, I should say, U epsilon here is the deformation, and epsilon denotes the fact that there is a small scale epsilon in the material properties governing this equation. So the stress, sigma, depends on a small parameter epsilon. And more generally, one can write for a large class of problems in viscoelasticity and plasticity, where the stress depends on the strain, the gradient, or the symmetric part of the gradient of the deformation, its time derivative, and its past history. And furthermore, because we have variation on a small scale, the stress tensor also depends on location x, will actually depend on x over epsilon, and on evaluation time t, which we will use to denote the fact that the past history it is indeed past history. So we only use the trajectory up to time lowercase t. So let me just simplify this for you for conceptual, just to give you a simple conceptual example to think about. The case of linear viscoelasticity and what's known as Kelvin-Voigt elasticity, there is no dependence on the past history. The stress tensor depends only on the gradient of the deformation and its time derivative, and does so in a linear fashion. Okay. Nonetheless, when you homogenize this, which is the next slide that I'm going to, you introduce memory. So even if there is not memory present in the original formulation of the problem, and there may or may not be, in plasticity there is, in some models of viscoelasticity there is, and in some there isn't. So Kelvin-Voigt there is not. Nonetheless, when you homogenize, there is almost always memory. And so the idea of homogenization is to find a field U0, which approximates U epsilon when the microphysics that underlies the material properties is averaged over, and identify an equation satisfied by the limit of U epsilon as epsilon goes to 0. And that's what I refer to here as the homogenized problem. So the key point about the homogenized problem is that the small scale epsilon has disappeared from the stress and therefore from the problem formulation itself, which enables much cheaper computation. But this is at the expense of needing to know the constitutive model that relates the homogenized strain, rate of strain, and strain history back to the stress. So with the group of Kaushik Bhattacharya, I'm interested in learning this map, psi0 dagger, from data. And that data is generated at the level of what's called the cell problem, for those of you who are familiar with homogenization. And this too is a problem in operator learning, in that the map that we're really interested in here is the map from strain history into stress history. So that's a map that takes, in this case, the deformation gradient, its time derivative, and the history of the deformation gradient, and returns the strain, returns the stress. So this can be learned using the methodology that I'm going to describe in a more abstract fashion in the remainder of the talk. So that's the second example motivating what interests me about operator learning. So speeding things up was the Navier-Stokes example. Here, trying to learn closure models or constitutive models for partial differential equations in continuum mechanics. The third example I want to give you, it returns to a question I raised earlier. So I mentioned that there are 4 sources of error: discretization, data volume, parameterization, and optimization. The point of this example is to show you that if you conceive of operator learning in what I claim is the right way, then it's relatively straightforward to obtain methods which are what I call discretization invariant. And the key idea here is that we conceive of architectures that represent our approximation of psi dagger. So this is the class of functions psi parameterized by theta. We conceive of them as acting between Banach spaces. And then if you do that, when you discretize, they will have a meaning. What you learn for a given theta will have a meaning at different levels of discretization. And it's possible to train at one discretization and then deploy them, what the architecture that you've learned and the parameter value you've learned, deploy it at a different level of discretization. And I'm going to show you that by means of this simple Darcy flow problem. So this is a problem for pressure V. I'm sorry, the velocity is not V, the velocity is A grad V. So this is just conservation of mass. And the constitutive law here, which we're not learning, so here it's known through the Darcy flow. The constitutive law says that the velocity field is given as A, which is the permeability, multiplying the gradient of the pressure V. I apologize for calling the pressure V, but V is pressure, or piezometric head to be more precise. The map that I'm interested in here is the mapping that takes the coefficient A into the solution V. Okay, so this is a linear PDE, but the mapping from A to V is nonlinear. Right, and the next slide I'm going to show you is a slide that is derived using one of the neural networks that I will describe in more detail in a few moments, based on PCA method. So this is computed using something, well, I've not got there yet, but when I get to the neural network, we computed using something called PCAnet. Before I do that, let me just show you a typical input and output. So typical input A is an L infinity function. For the experiments I'm going to show you, the permeability is a binary field. So you can think of this as a medium in which the permeability takes two different values. So you can think of something which is very permeable and less permeable. And the interfaces, which are defined by the measure mu on the data set, that these are the level sets of a Gaussian random field. So these are random input functions. This is one of them. And this is a typical output for the pressure. This is L infinity, which is not separable, but one can work in separable subspaces and thereby apply the theory, which I'm going to describe later on. All right, so we want to learn a mapping from a whole bunch of inputs like this to outputs like this. And this figure shows that we can do so. It applies the method called PCAnet that I'll describe in a moment. And what I'm showing you here is the test error relatively. So we're going from 3% up to about 4.5% as a function of the discretization of the input and output spaces. So the resolution of the input and output space discretization. And the color and the number that goes with it, D is 20, 50, or 70, is a measure of the number of parameters used in the parameterization of our neural network. So let's fix the number of parameters. Let's say D is 20. What you see here is an error of 4.5%. And crucially, that error is more or less constant with respect to the mesh resolution. Okay, so what I'm showing you is that the way that we will conceive of the architectures that approximate psi dagger, they are defined on function spaces. And as a result, provided what you train is accurate in the function space limit, it will also be accurate at different levels of resolution. And that enables you to really claim that you've learned something about the physics and the continuum problem, because what you learn can be used at different levels of resolution from the one at which you train. Now, then there's a second thing in this figure, which is that as I increase the richness of the parameterization, going from green to blue to red, I decrease the error. It remains resolution independent. And as I make the neural network richer in terms of its parametric dependence, I can bring the error down. And then finally, hidden in this picture is the dependence of the error on the volume of data. So here I'm using a fixed amount of data. And at some point, if you increase the parameterization without limit, you will not bring the test error down to 0 because you will have a finite amount of data. And actually 3% here is around the level at which the error from the data kicks in and stops you from reducing the error any further unless you increase the volume of data. So by this figure, I'm showing you that there's a complicated and interesting interaction in terms of the accuracy of these methods between the resolution that's used, the discretization of the Banach spaces that are input and output spaces, the number of parameters used in the neural network, and the amount of data. And that makes this a very challenging field, but understanding and disentangling the interaction between those sources of error is central to making this field one which is well-founded for use in scientific machine learning, in my opinion.
Hi, Andrew. Got a question from an audience member. You would like to hear it now?
Yeah, please. Yeah.
Okay, so Sean Sadiq says, okay, great. I wanted to know, were periodic boundary conditions used on the example of the Navier-Stokes on the torus? And are there limitations of the kind of boundary conditions Fourier neural operators can be used on?
Yes, good question. So this particular problem we're looking at now was Dirichlet boundary conditions and was not using the Fourier neural operator. So the question refers to this problem, which is formulated on the torus, and the specific computations that I'm showing you are performed on the torus. And the basic version of the Fourier neural operator is designed to operate on the torus. However, there is ongoing work which shows the ability of the method to be successfully deployed beyond that setting. There are a number of ways that that can be done. One is through embedding the domain that you do have in a larger periodic domain. And the other is to use transformation techniques to map from a periodic domain into something with more complex geometry and back again. I would say that state of the art there is, that's ongoing work. And you will see from my numerical experiments later that for the problems I describe, the Fourier neural operator is more efficient than the other architectures I'm going to describe, but that does not mean that as a general methodology, it is the most efficient method. And when it is most efficient is something that's going to be problem dependent, in the same way that we have pseudo-spectral methods, finite element methods, spectral methods, finite difference methods. And what the most appropriate method is problem dependent. In this field, we need to determine the answers to the questions, which are the best methods to use in a given setting. And I will describe numerical results towards the end of the talk that go towards answering that question empirically, but theory is needed. So the question is a very good one. The strength of the FNO, as I will show it to you here, is very much related to the periodic domain, but there is ongoing work to generalize.
Great. A couple more questions. So you can defer them to the end if you like, or I can ask to unmute one from.
Please, let's go. Let's answer them now.
Okay. So Constantine, if you would like to unmute.
Yeah, Andrew. For the porous medium problem.
Yeah, hi, Constantine.
Do you have a heuristic as to, yeah, the next slide, right? I mean, you need some level of resolution or you're not going to get started. So given that you know the equation, do you have a heuristic that would tell you what resolution you should start looking, and the kind of the same question at you know, if I gave you arbitrary amount of data, you know, the relative test error at some point is just, it's already kind of bottoming out is what you're suggesting.
Yeah,
right?
so
these class of problems.
All of these are well resolved, and the question is really a question in standard numerical analysis of PDEs. At all of these levels of resolution, we're describing the continuum limit pretty well. So then what you see here might look a little bit trivial, but it's not, in the following sense that there were some very clever methods for training, in fact, explicitly on this problem, training at specific levels of resolution, but they didn't transfer between different levels of resolution. So there are pre-existing methods which would work on one level of resolution, but you learned nothing when you tried to use them on a different level of resolution. So the fact that things are invariant under resolution really means that all of these resolve the PDE accurately from the point of view of numerical PDE, but it is a consequence of the way we design the methods that you can move smoothly between different levels of resolution, and what you learn at one level of resolution, provided it's sufficiently well resolved, tells you something about other levels of resolution. Okay, that's, I think, the right answer to this question. Now, a retort to that could be that many problems you cannot resolve fully the physics because of microscale structure. And that's the reason why I'm also interested in learning constitutive models, as you saw in the discussion about viscoelasticity and plasticity. So learning closures is a way to deal with that issue. Thanks.
Thanks.
Okay.
Thanks, both of you. And one last question, but I think you answered this in your previous discussion there. Ashk asked, the resolution shown in the last shown slide corresponds to the grid resolution of permeability.
That's right. It's the grid resolution used in both the permeability and the pressure spaces.
Okay, that's what we have for now. So thank you very much. Please continue.
Thank you. Okay, so now I'm going to get into a little bit more detail of what the algorithms look like, and then specifically what the architectures look like and how the function, the operator classes psi, how they're built and parameterized, and it's the approximation theories that are developing around them. So I'll give you a view of what is known. And so let me first start by talking about the PCA net, which was used on the porous medium flow problem. It's a very simple idea in words. In words, the idea is that you have data in the input and output spaces. You use principal components analysis in both input and output spaces to find finite dimensional latent spaces. And in those latent spaces, you learn a neural network. And written in math, you get an architecture of the following form. And y is the independent variable in the output space. So u is the input function, and LU is a set of linear functionals. In this case, they are the coefficients of u in a PCA basis computed from the data, or a finite set of PCA coefficients. And this is a neural network that takes that as input and is parameterized by theta. And then in the output space, which is where this whole object lives, we work in the linear span of the principal components analysis basis functions in the output space. So to implement this method, you do PCA in the input space to compute the inputs. You do PCA in the output space to compute a linear span in which you approximate the output function. And then you train neural networks that depend on the linear functionals of the input and use them as coefficients in the output basis space. So I'll show you that in a picture. We're interested in going from Banach space U to Banach space V, and psi dagger is the truth. And what we're doing with PCA is it's a basic autoencoder, in fact, if you like. PCA is an approximate factorization of the identity. So G composed with F, GU composed with FU is an approximate identity on U, and GV composed with FV is an approximate identity on V. And these are the latent spaces through which the approximation is constructed. And then the neural network has the following structure. One uses the encoding FU of the PCA analysis on the input space, trains a neural network on the latent space, and then decodes to get the solution in the output space. And in this work with Kaushik, Bamdad, and Nick, we showed a convergence result for this approximation. And this is in the form of a universal approximation theorem that shows that from within this class, PCA, one can approximate psi dagger to arbitrary accuracy epsilon in this Bochner norm, which is an LP norm from U to V weighted by mu. And here I've averaged over the training data that we are given, or average over the distribution of the training data. So the key thing to recognize about this theorem at a high level is that it shows that for this neural network, we can indeed approximate a wide class of operators between Banach spaces. That's the plus, and I'm going to show you several results of that type. The negative is that it doesn't really tell us very much about how hard the problem is. It doesn't tell us anything about the complexity. It avoids completely the issue of optimization and finding the best solution. It simply says that within this architecture, there is a solution that achieves epsilon approximation. So that's good, you would want that. But if you compare it with the state of the art in numerical PDE, where we know how much it costs us in terms of how expensive it is to run the model as a function of the error we want to achieve, that's a crucial aspect of numerical PDE that we do understand that. We understand the relationship for many basic problems. We know how much it costs to run a model as a function of achieving error epsilon. That is not part of this theorem. This is simply an existence theorem that says we can achieve, in principle, error epsilon. It doesn't tell us how to do it, how to find it, just says it's within this class, and it doesn't tell us how much it will cost to run it. Okay, nonetheless, it's a very positive result, and one would want results of this type, and they exist, as I'm now going to show you, for many other operator approximators. Now, one thing I want to point out about this method, it's slightly non-standard compared with regular neural networks, in the sense that these encoders, which are computed with PCA, by the way, there's a theory for PCA on Hilbert spaces, and so necessarily U and V are Hilbert spaces for this theorem. There's a pre-computation involving PCA, and then that defines the decoding G and the encoding F that are part of this neural network. And then you train the neural network var phi on the finite dimensional space. But you might say, okay, well, let's see if we can do better. Rather than specifying GV with through PCA, let's try and learn GV. And that brings me to a class of methods called DeepONet. Now, these mathematically in math have very much the same structure to PCANet in the particular formulation that I'm using here, with the difference, important difference, that rather than specifying the output space to be in the linear span of the PCA basis functions, we instead learn the output basis functions from a parameterized family of neural networks. And that gives greater flexibility, and in principle includes PCA if the data is rich enough. So this should be a better method than PCA in general in terms of expressivity. This method has been extensively developed and shown to be very effective by the group of George Karniadakis at Brown. There are a number of papers on it. Here I highlight one of the first papers to come out of that group in this area. And also to mention that the method is a generalization of something that appeared in the early 90s in the electrical engineering literature by two authors, Chen and Chen, and was developed essentially by making it deep and then various other innovations that make it computationally tractable. So one can ask now, how about universal approximation for this variant on the PCA method? And there are many theorems around DeepONet, and I'm going to quote two that come from the thesis of Nick Kavatsky, who is a graduate student at Caltech, who graduated this week. Nick has made some profound contributions to this area, and two theorems which apply to the DeepONet as I've shown it to you, but also to the neural networks that come subsequently on the following slides. There are two kinds of theorems here, both of universal approximation type. Namely, they show that we can achieve error epsilon. And the first one is a fairly standard form for those of you familiar with universal approximation in finite dimensions, in that it looks to approximate over a compact subset of U, and within that compact subset, one can achieve error epsilon. So that's very much how standard universal approximation is formulated for neural networks between Euclidean spaces. And it's based on the approximation property, which states that any compact operator can be approximated by finite rank, by limit of finite rank operators. And this is a property of many Banach spaces, including all Hilbert spaces, little LP spaces, and anything where you have a Schauder basis. So it's a fairly rich class of Banach spaces that have this property, but it is not all Banach spaces. Excuse me. Then one can also look at the error in a slightly different way. So this works over a compact set and achieves error epsilon. An alternative formulation and assumes psi dagger to be continuous and is very analogous to finite dimensional theorems. The second theorem of Nick's is formulated in the setting where psi dagger is an LP function from U to V, and therefore now achieves an error by integrating with respect to measure mu over the whole space, again to achieve error epsilon. And in rough hand waving terms, one can combine compactness with tail estimates for the probability measure to extend this theorem above, the first theorem, which holds on compact sets, to one which holds over the entire domain. I should also mention there's lots of theorems about DeepONet and its approximation capabilities. There's important work of Sam Lanthala, Sid Mishra, who are at ETH with George Karniadakis, which establishes theory concerned with this method. And then I will come back to further work that these guys have developed that's more general than DeepONet.
We have a hand raised, Andrew, so
Yes.
I'll ask to unmute.
Hi, Andrew. I have a question so that I understand. And so you refer to classical universal approximation theorem. The original ones, they're shallow, and then you have a sum over some sigmoidal functions. And then the deep ones is the composition of functions. Should I understand your theory as the analogs of the shallow networks, or because I don't see compositions of operators here?
Thank you. Good question. Firstly, this is not my theory. It's Nick Kavatsky's theory. So I just want to be clear about that. Secondly, in this theory, the composition is not used in an intrinsic way. Can be used, but it's not intrinsic to it. And the main innovation here over finite dimensions is the use of the approximation property, which you can think of in pictorial terms as being the analog of these autoencoders that are used in input and output spaces to find a finite dimensional latent space. And that is I think the primary innovation that underlies these two theorems. However, in answer to your question about composition, you will see that when I go to the Fourier neural operator in a few moments. Thanks. Okay, I wanted to mention Paranet, and again, there's a formula for this, but let me just try and explain it to you in a very simple way. All of the previous methods viewed the function, the psi, the operator that we were trying to find, as a function from one Banach space U of functions to another Banach space V of functions. But functions in V are, this should be RDO, they're vector valued functions over domain D. And so it's also possible to view the operator as a function which takes U crossed with the domain of the output space and maps it into the vector valued output. And now you can then look at taking linear functionals in U and training a neural network which operates directly in this way. And that's what Paranet does. Now, in principle, Paranet includes DeepONet. So I've gone through a hierarchy. PCANet was a subset of DeepONet, and DeepONet is a subset of Paranet. And Paranet has the advantage of being what's called a nonlinear approximation, meaning that in the output space, the space in which we seek the solution depends on the input. And that's not true of either DeepONet or PCANet. The output space here is independent of the input. So this is what's called a linear method in terms of approximation theory. Paranet is a nonlinear method, and it's known that nonlinear methods are needed to beat a cursive approximation known as the Kolmogorov, that goes associated with Kolmogorov n-widths. So there's a potential advantage of this method, but as I will show you by means of experiments in a couple of minutes, it's not competitive in terms of cost per unit error. But it does introduce the interesting concept of nonlinear approximation. And that leads me on to the final method in answer to Mohammed's question, an example of where we use composition in the way that deep composition is used in standard deep neural networks. The Fourier neural operator is a neural operator which is comprised of a number of operations which are all pointwise, either in physical space or in Fourier space. And it has the structure of a standard deep neural network with, namely, this compositional form that Mohammed referred to, with two particular innovations that I want to highlight. So I'll come back to the second one, which relates to R and Q in a moment, but let's just concentrate on the composition of these layers L. Each one of these layers looks like a standard layer of a deep neural network in the sense that it's computed with a activation function, sigmoid, which is applied pointwise to a linear transformation of the function V. That linear transformation, however, is non-standard in the following sense. V, remember now, is a function. We apply a matrix to it. So this is a pointwise linear transformation here. So that's fairly standard. And this here is, in general, an integral operator. And if it's translation invariant, you use the convolutional structure, you can compute it via FFT. And so this corresponds to pointwise, the second corresponds to pointwise multiplication in Fourier space. And therefore, as a consequence, everything in here is pointwise, either in physical space or Fourier space, and is very cheap to evaluate. And you can use the FFT, noting the question we had earlier about restriction to periodic domains. You can use the FFT to move quickly between the two pictures. So these layers are evaluable very quickly. And this is combined with R of U, which is a pointwise neural network, which lifts the output dimension of the vector valued functions U that are in the input space. So to be concrete, imagine that U is vorticity, which is scalar valued. This would lift it up, typically in our examples, to something of 20 or so dimensions. So rather than having a scalar valued function, this through a learnt neural network, which applies pointwise in physical space, would lift up to a vector valued function of higher dimension, and cube maps back down again. Why we do this is empirical observation that it's better to put parameters into this lifting than it is to put it into increasing the number k max of modes considered in Fourier space. That's purely empirical, and theory related to determining whether that is indeed the right thing to do is much needed. And that is an example of a more general question. It's not just the number of parameters that we put in, it's how we construct the architecture and where we put the effort in terms of parameters. So I'm just telling you that empirically, for the problems we've looked at, it's better to put parameters into lifting the dimension of the input function, which is, say, scalar valued, lifting it to R20, for example, than it is to increase the number of Fourier modes that we use in the FFT part of this architecture. But that is empirical, and there's no theory. There is some of the earlier theory of Nick Kavatsky I described applies to this. And there's also some interesting work of Kavatsky and Sam Lanthaler and Sid Mishra, who I mentioned earlier, which studies the curse of dimensionality for this problem. And their methodology is to show that this method can mimic pseudospectral methods. And this is a general methodology used to analyze many problems in this area, showing that neural networks can mimic existing methods. That's nice from an analysis point of view, but really is somewhat disjoint from the power, I think, that neural networks exhibit, which is almost certainly exhibited by going beyond what standard methods like pseudospectral methods, finite element methods, or wavelet methods achieve. Nonetheless, it's a method of analysis that's widely used to show that the neural network can mimic an existing approximation method. And in this paper, amongst many other things, the three authors show that the Navier-Stokes equation can be approximated and the curse of dimensionality beaten in a way that's made precise in that paper. Okay, so I'm going to wrap up with just showing you some very quick examples. I've tried to indicate that there's an interaction between a number of competing fields. I've shown you that there's some theory, and I've shown you the good motivation, I believe, for doing operator learning. but I have not shown you good theory that tells us which is the right method to use and in which situation. And that's because that theory doesn't exist. And just to show you how it might be hard and what the theory might look like, I just want to show you, return to the Navier-Stokes example, but now I'm going to look at mapping from forcing to vorticity. And I just want to show you these figures and just concentrate on the red curve, which is for the Fourier neural operator. These curves are plotting the error against the evaluation cost of the method. So this is something which we theoretically understand from many methods in numerical PDEs. How much does the evaluation cost increase when we demand that the error goes down? You see for the Fourier neural operator, there's a clear curve. I'm doing this for different levels of data training, but in all cases, you see a curve here which relates the cost to the size of the error. It's clear evidence of a theory which will explain the complexity of this method in terms of how quickly this curve decreases. But there is no theory that fully explains this. As an aside, for this specific problem, the Fourier neural operator has much more desirable properties than the other methods. That does not mean it's the method of choice for the reasons discussed in answer to the very first question. This is a problem that's been designed for the Fourier neural operator because it's on a periodic domain. But what you see here also for Paranet, but there's some overfitting for the others. The most important thing is there's evidence of a theory that shows that for this problem, there's possible theory to relate cost to evaluation. Evaluation cost to error. But I want to show you that for the advection equation, things are not so rosy. And just to give you an idea of some of the limits and where innovation is needed. So this is a very simple problem where we just map initial condition to solution at 0.5 time 0.5. These are typical median solutions at median test error, but these are failure modes. And I'm showing you that all of the methods fail in this case. And if I plot the error against evaluation cost, you see that the story here is not so rosy. And the reason for this is related to the lack of regularity of the functions in the output space, which is discontinuous. Okay, so I'm grateful to you for having listened for the last hour, and I've managed to finish on time. I'll just leave these conclusions up here for you to look at, and I'm happy to answer questions. Thank you.
Awesome. Very interesting talk, Andrew. Thank you very much. So we'll open the floor. Anybody who would like to raise their hands, we can unmute, or you can type some questions into the chat. Okay, Mohad, go ahead.
One more question. I'm sure you've thought about this. So I want to see if you want to share your thoughts about this. If you have conserved quantities of your PDE, is it easy to enforce it in this work? So the learned operator respects those.
Very good question. We've thought about it. It's not part of anything you've seen here. One thing we are working on, which is not related to conserved quantities, but rather to dissipation, we're working on the neural networks that we trained for the Navier-Stokes equation are accurate on the attractor, but off the attractor, they can suffer blowups. In contrast to the Navier-Stokes equation itself, which is dissipative in the sense that any bounded set in L2 is mapped into a compact set, the same compact set, independent of initial conditions. So we are looking at ways of either through training or post-processing enforcing dissipation inequalities on what we learn. So that's something we have been doing.
Right.
There is also really interesting work coming out of George Karniadakis' group showing that it's possible to develop symplectic neural networks. So those, as you can imagine, will be very useful for certain Hamiltonian problems because they will reproduce symplecticity and therefore all the conservation laws that come with that in terms of projected areas.
Right.
But I think there's a lot more to be done in this. And so, yes, we're thinking about it, but nothing major to report.
Thank you.
Thanks.
A few questions in the chat window here. Pedro asked, beyond the discretization invariance in the sense of posteriori evaluation of the method on different discretizations, do you have discretization invariance or control in the sense of comparing the performance of your model when it has been trained on different discretizations? Did I read that in a way that can be understood?
Yes, that's a very good question. Yes, so we have done experiments, not shown here, where we've trained one level of resolution and used what we've learned at other levels of resolution and shown success in doing that. So, and going beyond that, we've found that that can be very, in problems where you don't necessarily know the model form or the appropriate architecture, that can be a very useful way of determining whether you're working within a sensible architecture class. So I think it's a very, if you're working in settings where the continuum limit is well defined and tractable, but expensive, I think that it's a very important concept to be able to be mesh invariant and to be able to learn something at one level of resolution and use it another. And indeed, we've shown that you can do that. Thanks.
Awesome. Just a couple more quick questions. One person, simple question, asked if they would like a copy of the slides, how can they acquire them?
Yeah, so I can, if you have a website associated, I can give it to you and you can put it there, or otherwise you can just email me and I'll send it.
Okay, perfect. We'll figure that out post talk. And yeah, maybe email is the easiest option for individuals. So Lucian Ivan asks, great talk. Any thoughts regarding the application for solutions with discontinuities?
Yes, I mean that was I was rather rushed at the end, but that's the issue with the very last example I gave of advection. There are a number of directions one might go with this. Let me just mention one, which is work of Sam Landhaler, who I mentioned several times during the talk. He gave a presentation at SciMUQ recently that showed a generalization of, let me just go back with my slide, a generalization of DeepONet in which psi j is allowed to depend on the input data through something that is a translation and scaling function. So it's rather like the idea of wavelets, that you have an outer function psi j, but the function is evaluated at translations and dilations that depend on you and are learned. And they've had some success with advection problems with discontinuities and with Berger's equation using that method. So that's one idea that looks promising. There's work in Karniadakis's group in this direction. So I think it's something that where you will see a lot more activity. It's not settled, but it's clearly, from an applied point of view, an important direction. There are interesting problems that, to me, in continuum mechanics that arise from discontinuous material properties and the effect that they have on the stress, that are discontinuities and derivatives, for example, rather than in the function itself. So I think this is something that needs further investigation. Thank you.
And Andrew, whenever you are tired of answering questions, please let us know. There's about 3 more in the chat.
No, I'm not tired. It's good. I'm happy.
Awesome. Okay, so Alexander Litvinenko asked, do you see any similarities between low-rank tensor methods and neural networks, especially for multi-parametric high-dimensional problems?
Yeah, so I think maybe high dimensional here could even be extended to PDEs which live in high dimensions. I think in that particular direction, so think of Schrödinger equation or Black-Scholes equation. I think in that case, use of tensor methods to represent the input space is something that's very likely to be useful in designing architectures that will make competitive methods. So that's one answer to the question. Secondly, you can ask the question whether neural networks could mimic such low-rank tensor methods. And that may be the case. It's not something I have much knowledge about, but I guess that in principle that is possible. But I see that direction as being most relevant for PDEs where the dependent variable is in a high spatial dimension, high dimension. Thanks.
Awesome. Okay. Cristobal Alvarez asked, hi, I have a question. Does the overfitting phenomenon occur in this type of architectures? And he says, thank you for the great talk.
Thank you. Yes, it does occur. So I can actually show you the overfitting. So on this Navier-Stokes problem, let's fix on at 5,000 data points. The red and the orange are FNO and Paranet, and both of them do not suffer from overfitting at this data level. However, Paranet, PCANet and DeepONet both suffering from overfitting. So as the evaluation cost comes down, this is as the error comes down, the evaluation cost is going up because we're parameterizing more richly, but eventually you've hit an over parameterization regime and the error starts to go back up again. And that can be ameliorated by increasing the volume of data. Here you see that it's leveling out. I would anticipate that all of the methods potentially suffer from overfitting. It's just that for FNO, we don't see it at this level of data and we see it later because it has a more parsimonious parameterization for this problem, for this specific problem. But in general, overfitting will often be there. And your question is a very good one because I think it comes to one of the big challenges in this area is to understand not just the sources of error, but how they interact. How should we choose the volume of data as a function of the parameterization to get a given level of error? Now, there's really interesting work, for example, in multi-level Monte Carlo coming out of, starting with Mike Giles, which indicates that in that case, it's the interaction between Monte Carlo approximation and discretization, and organizing the computations to take account of relationships between errors through sampling and errors through parameterization or discretization. We know from multi-level Monte Carlo that can have an enormous benefit in terms of complexity improvements. And the same things I anticipate being true here. If we know how to organize the computations for different discretizations, different volumes of data, and different parameterizations, if we understand how to organize the computations theoretically, we will be able to improve complexity in terms of cost versus error. So I think that's one of the really big challenges for this field. Thank you.
Awesome. I will let somebody else speak. So I'll unmute Sean Sadiq.
Yes, so on the Gaussian random field, what is the significance?
I'm sorry, Sean, you're very quiet to me.
Oh, whoops. How about now?
That's good.
Oh, yes. So on the Gaussian random field, what was the significance of having the shifted Laplacian there? Like, what was that?
So the shift introduces a length scale. So tau is an inverse length scale. And roughly speaking, by controlling tau, you control the length scale of typical draws from the Gaussian random field. You can be more precise about that, but that's roughly what it is. Another way of looking at this, this is closely related to a Matern random field, exactly related to a Matern random field in some certain cases, and tau would be exactly the inverse length scale in a Matern, and delta shifted by constant would be the regularity in a Matern field. So that's the short answer to the question. You can control the length scale by playing with tau.
All right, great. I think we're down to just a couple more questions from MZ. He or she asked question one, is any preference on activation functions when training neural nets? And question two is the training done with noise-free data?
Thank you. Both really good questions. We have found that the choice of activation function matters, as in changing it sometimes leads to improved results, but I do not have any even empirical understanding of what a good choice is. So it matters, but I don't understand it empirically and even less theoretically. I would like to do so. That was the first question. What was the second part?
The second one was about is the training done with noise-free data?
Ah, yes. So in this setting, the training is done with noise-free data. So that also it leads on to an important question. So here, in these problems where you actually know the PDE, that the ones I've shown you, and you generate the data by a numerical method, pre-existing numerical method, you have a choice of, it can be noise-free up to discretization error, but you have a choice of measure mu. And choosing the measure mu for a particular design objective is something also where I think there is need for work. So it's a kind of optimal design problem. When you can, in this setting, in contrast to scraping data off the internet, in this context, we can control mu, we can choose it, and we should choose it cleverly for the tasks that we want to use our neural operator for. And we do have examples in constitutive model learning where we have rules of thumb about how to choose the measure mu, which empirically can be shown to lead to better training for the tasks we want to use the surrogate model for. But again, this is something where, at least here, we have some empirical understanding. Theory is also needed. Thanks.
Fantastic, thank you. And I think we can finally ask the last question here. Lucian says, where should he email to ask for the slides? Your administrative assistant, or and also I should note, we will post the recording of the talk, if that's okay with you, on our YouTube channel for the future. Yeah,
that's fine. Yeah. You can just email me or my admin assistant, whose name is on the webpage. I can put my email here, but I'm only, hang on, everyone. Okay, let me just write it. So it's in the chat.
Okay, so I can, to everyone, perfect. Okay, well, Andrew, thank you so much. It was a fascinating talk and some great questions as well. So thanks to everybody, and that will conclude our seminar for today. And we'll send out a new reminder for our next speaker, whoever that might be. Okay, thank you.
Thank you. Thanks everyone for the great questions.
Bye-bye.
Bye.